and what you see on this frame is the actual windmills on the wind farm called Greater Gabbard on the North Sea, just close to the English shores. And there are these points represent the windmills. As you see, they are corresponding to the these red rectangles in the Landsat imagery. There is also a tiny cloud in the middle, and on the left side, a container vessel up there. So what is worth underlining there, this, what you see up there, it's just a image taken by a satellite built from scratch with a company which hasn't built a EO satellites before. And it's basically our tech from 2018. So this is not the commercial imagery we're providing. So that's a like our development process. That's worth remembering. So let's get to the next slide, please. About an overview of technical parameters of the whole payload Vision 300. So what's in there? What Vision 300 consists of? So first of all, my view switched to our clean room live view. Are we still on the presentation slides?
Yeah, we're back in a moment. Just give me a second.
Okay, okay. So just a quick view on our clean room, which is not occupied at the moment, because that's quite an evening in Poland up there. So do not expect a huge action, and I believe we're getting back to the presentation. Thank you, Grzegorz. So getting back to the technical parameters, there are just two main components, which is camera based on the commercial off-the-shelf CMOS sensor. It could be delivered into in the panchromatic version. So with just one broadband, and then with Bayer filter. So the outputs are RGB and the near filter. There is also a onboard memory. So this is a information which has been corrected since the previous presentation. So there is a 64 up to 64 gigabytes of the flash memory, and not FRAM memory. Someone basically found a typo up there. So thank you if you're there. If you're not as well, thank you. And the lens is a Cassegrain lens with low dispersion. I won't get more into the details of the lens because Piotrek will tell you in details what's up to with the lens. And what's the most interesting here is that the whole payload is basically a CubeSat form factor structure. So the technical parameters of the output imagery is GSD 5.8 meters at 500 kilometers. The angle of view, which gives a field of view of 14 at times 12 kilometers at 500 kilometers. That's an approximate. It has a focal length of 300 millimeters, and the following parameters are, I believe, kind of well known to everyone. And so there is different processing output from the camera. The image resolution is basically a byproduct of the sensor resolution. So this is an actual resolution of an image frame delivered to Earth. the operating temperature. This is the temperature in which it's operating like basically inside the satellite. So that's operating temperature of the camera, which has been proven on LEO that it's around 30 plus minus 5 Celsius degrees. From the physical properties, there is worth underlining the camera interfaces up there. So there is gigabit Ethernet and USB, 12 megabits per second. And the input power, 3.3 watts at 12 volts, that's maximum. So all the qualification tests has been done, and basically an in-orbit demo as well. So let's get to the next slide, please.
Tomek,
can I ask a question or should I wait for it?
Question. So first question is, how did you manage to thermal expansion or materials oval lens housing?
Piotrek, I believe that's the question you will be answering through your presentation, right?
Yes, I'm waiting for my turn.
Right. So
May I ask one question here, please?
Yeah. So Maciej, please wait a moment. There is Piotrek's part coming in a moment, so it will be well answered.
Yes, and there is a second question, Antix, from Kies Rayu. It is a panchromic image with a reflective lens, unique reflective.
Oh, that's the question I don't really understand. Yeah, that is a panchromatic image, and what is up there with refractive lens, unlike reflective. That's a reflective lens rather than refractive. So the whole telescope, it's using the reflection instead of refraction. So if that's an answer to your question, Raju.
No, what I was asking is, are you able to hear me?
Yes,
we can hear you.
Yeah. So two questions. One, what I was when you mentioned it is as a lens, the panchromic image that you have seen is through a reflective optics or through the lens that you have mentioned.
Yes, the panchromatic image which you have seen on the slide on top of this Landsat RGB image. So this panchromatic one was took actually with the IRIX 300 SR lens on board of Światowid, and this
so it's a refractive lens. It's a refractive camera.
It's a combination of reflective lens and refractive lens. It's a catadioptric design.
Okay. And just this the technical parameters side, you have a operating temperature of 5 to 45 degrees for the camera, but the qualification test has been done from minus 40 to 120 degrees, which is beyond the operating temperature of it. So does it, like, how does it survive that extreme thing? And thing is, why do we need to go to that extreme when your operating temperature is only 30 plus minus 5 degrees?
So the story is following. All of the system has been put through the thermal vacuum cycling at this like extreme temperatures, right? But the camera wasn't. Hasn't been operating in this thermal vacuum cycling temperatures, and the proven operating temperatures at LEO were around the spectrum of its operating temperature, right? So the camera hasn't been touched by these extreme temperatures like minus 40 or 120 or even close.
Yeah, so when it is not operating at that temperature, should the thermal cycling be within 30 plus minus 5 means 25 to 30, or probably a little more margin, maybe like 20 to 40 degrees? Should that also qualify the package to operate?
I think we should distinguish the meaning of the operating temperature instead of surviving temperature. For example, if we talk about the lens construction and its parameters, its best optical parameters, they are kept in very narrow temperature. For example, a classic landscape lens is designed to work under under temperature from +10 degrees Celsius to +30. That's the temperature range that provides the best optical performance of the lens. Of course, the lens will work under lower temperatures, even when there is on minus in Celsius. But I think we should talk now about what kind of temperature we are talking about. If we talk about the temperature that lets the devices and optical payload survive. For example, when during the lift-off and when the satellite is high in the Earth shadow, and what happens next when the satellite go outside from the Earth shadow and it's illuminated by sun. The temperature may vary across very huge temperatures.
Yeah, so those are extreme temperatures, but if you have any thermal management system, which will make that always the operating temperature is within the specification of 30 ±5. In that case.
Yeah, I'll talk about in my presentation, just a second.
Okay, thank you.
Yeah. So,
okay, I think we can move on because there is only one more question from Maciej. Are there any special accounting you applied? If the Piotr presentation will answer this, we can move forward. If not, maybe we can answer right now.
It's not a problem, of course.
Yep, it will be in Piotr's part. So let's proceed. Okay, so basically I've presented this before, just to underline this sensing element could be brought into the options. So there is option of panchromatic, the RGB and near. So basically your choice. What if you're like looking for a payload for Earth observation, you're picking which one you need for what specific needs. So we can get to the next slide, please. And from the standpoint of physical properties, what is very important, this is that the whole the size of the whole optical payload, the whole Vision 300, it's a 3/4 of unit, and the mass do not exceed 500 grams. So according to the standard, you still have some unused mass for a different component at your CubeSat. So there is still some mass to be used. So the next slide, please. Okay, I believe we got to the time where I should pass the microphone to Piotr. So thank you, and Piotr, if you're starting there.
Okay, thanks so much for the introduction. At first, I will try to characterize the lens, and after, if somebody will have any questions about the optical construction, about the other details, so please write it on the chat or just use your microphone and ask me. When StarTech designed the RX300 SR for Światłowid satellites, we got a very tight brief from Tomasz. The lens has to be very small. I mean, its outer diameter should not exceed 70 millimeters, while the length of the lens should not exceed 80 millimeters. That was the two parameters regarding the size, but the rest of them were also very tight. what we were aiming to obtain 300 millimeter focal length that will allow to get a specific field of view. After obtaining the focal length of 300, we should keep the lens aperture as high as possible, but not lower than f5.6. It's because to keep the circle of confusion as small as possible to provide the full compatibility with the pitch size of the pixels in the Sony previous sensor. After a few months of optical design, we got a scratch of the lens, which represents very good optical resolution. After our test with color Bayer sensor, the lens provides up to more than 50 LPM at this moment, but this is still subject to update. What's more, the biggest problem when designing the lens was simplicity of the satellite construction. We didn't have any possibility to change the focus after the assembling process, after the combination of the lens with the satellite. The payload must work in various temperatures, must manage the vibrations and shock during the lift of the orbit. So we decided to make a safe design. I mean, the safe, I mean the design that will keep the optical parameters for a long time. That's why we decided not to use any kind of focusing mechanism. The only focus adjustment is provided by adjusting adjusting the BFL distance to the camera, because some cameras, each camera has different sensor, has different thickness of air filter on over the photodiodes. That's why we designed to make the lens exactly tailored for the sensor of Światłowód. Regarding the question about how we manage the thermal expansion and material of the lens housing, it was a very big problem, because there is no possible to install on the satellite board any kind of mechanism that will allow us to post focus to check if the focus is okay. The only way to check if the lens is properly calibrated for the mission, it was to make a photo from space. That's why our optical engineers, when he got the brief, he know that he must provide a very wide tolerance for any changes of the lens housing size. I mean, it's also the tolerance of the optical surface thickness. I mean, the distances between lenses, also the thermal expansion of the glass, of the metal. That's why the lens, we try to make the lens that will survive a wide range of temperatures, and also the work in the high vacuum space. So there is no any special features inside the lens that provide that any kind of active calibration that will help us to change the focusing distances. So we decided to at first to wider the tolerance for optical design, the same for mechanical design, but we also use the materials that are accepted by NASA for space purpose. Can you go to the next? Oh no. Let's keep the same slide. Basically, the lens was made with C-mode camera, the same as the camera which is on board of the satellite SatRevolution. But after that, we decided to make the second version of IRIX Space Lens 300 SR. It will be codenamed 300 SR2. Please go to the next slide. Thank you. Next one. Can you go next one? Next. One more. Oh, thank you. Here we see. Oh yes, this one is okay. Here we can see the lens in the second version that has replaceable lens mount that allow us to check the optical performance with different camera sensor. Because checking how the lens will work with industrial camera, it will be expensive and sometimes hard to get such kind of camera. That's why we decided to use a photographic mounts to check how the lens will perform on different sensors. Yet today we tested the lens on micro four tilt sensor, on Sony A7 sensor, and others. This will help us to check how the lens perform in the ground laboratory test on the using IMA test and other metrology equipment. Is there any questions about the lens? There was a question about what is the kind of optical design. The lens is a catadioptric design which combines reflective and refractive optics. The aperture stop of this lens is 5.6, but in theory, if we look at the optical design, the f-stop of the lens is 4.9, but we need to take into account that there is a central obstruction of the lens aperture. So the final f-stop of the lens is 5.6. This means we are still have the lens that is practically diffractive limited at 7 microns. And for another questions, what is the circumference diameter? Can we go to the slide before? Okay, thank you. No, the one, next one. Not this, sorry, not this one. Yes, oh, exactly. The first version of IRIX 300 SR has a circle diameter of 28.4. The lens was at first designed for APS-C sensor format. This will allow us not only for test the lens in the ground laboratory, but also to use cameras on board on the other satellites that has a major imaging sensor. In the second version of IRIX 300, that's the version which will be lifted to space in December this year. We will try to expand the optical, the image circle to 30.1 millimeters. So the max, at this moment, the max image circle is 28.4, but we are trying to take the best from the optical design and keep the largest possible image circle. What's the mechanical interface between optics and housing and vibration levels for the testings? The mechanical interface between optics and housing, what's the mechanical interface? My question is to Chris Raju. What do you mean housing? Do you mean the camera mount or the aluminum housing of for the lens, glass lenses.
No, I mean the optics and the mechanical housing.
What's the mechanical interface? Lens, you mean how the lens?
Yeah, lens and the aluminum housing is probably it is the entire lens housing. I'm talking individual elements. How does it mount?
Yeah. Okay, thank you. I understand now. While designing the mechanical part of the lens, we tried to we try to position the lens. It's hard to, for me as not an optical designer, it's hard to explain, but our designer tried to reduce the amount of surface that provide a connection between glass and the metal. That's why while the aluminum housing is expanding or it's shrinking, the lens position is maintained the same. Of course, there must be some difference when the lens is very cold and very cold because of the temperature changing. That's why we decided to make some improvements to the IRIX 300 SR2, which I will explain using the next slide. Can we go to the slide with the temperature? Yeah, that's why. Here is the simulation that we will make using our optical design. The blue line represents how the backfocal length of the lens, I mean the distance between the last optical element and the image sensor plane, how the distance shifts depending on the temperature change. As you can see, there is almost 0.3 millimeters change across the 30 degrees Celsius. So that's the change that we could not manage without an active athermalization of the lens. So we decided to keep the design the same as previously, but we will try to estimate what is the best moment to make pictures where the optical quality, the optical collimation of the lens is the perfect point. I mean, the lens was designed to work under condition of plus 16 degrees to plus 27, if I could remember. That's the temperature range that should provide the best optical quality of the payload. That's all we could do using such small amounts of place for the lens in the optical payload design. Please go to the next slide. The one more improvement to the second version of IRIX 300 SR we made is we added place for NTC thermistors. These thermistors were absent in the first version of the lens, but we decided to add some space for them because it's very important to monitor the lens temperature across the mission, to monitor how it changes depending on the Earth. So the information from thermistor will tell us how the temperature of the glass elements change. If it's steady after some time when the satellite goes out from Earth shadow, for example. So using the safe optical mechanical design and have such small place to add any kind of active or even passive athermalization, we will try to manage this with choosing the right moment for taking pictures. Of course, this is not a final design. We will try to collect the information about the temperature to use it in the next mission, maybe in the version SR3. We will know more about the temperature fluctuation, and we will improve the mechanical design, or we will have more knowledge about how to provide passive athermalization, or maybe use some kind of thermal conductive materials. Is there any questions more? Let me check. Can you share some information about MTF and distortion values? The final optical resolution of the lens, also the rest of the optical parameters and characterization, they are still subject of tests of some kind of improvement. Due to some patent reasons, we cannot share more information about the exact optical design, also how it looks like inside the lens, and what kind of solution we introduce to the lens. I think we will do our best to provide more information close to the end of this year, when the design and testing procedure will be finished. I forgot to add that there is one more improvement to the SR2 version in comparison to the first RX300 lens that still sits on board on Światowid satellite. We also add a fourth ventilation channel that should allow the lens to equalize the internal pressure. In the first version of RX300, it wasn't airtight, it wasn't hermetic in design, but we think that adding some kind of pressure equalization channels will help the lens to put out the internal pressure, to equalize it with the vacuum in space, which may cause some kind of distortion, I mean, of the main lens. The mounting of the lens is very sensitive. Of course, it's not sensitive for vibration and for temperature fluctuation, because the lens was already prepared for this. But if we try to calculate how much, what is the force of the air inside the lens put to the lens, there's a 20 kilograms of force put on the main mirror of the lens. There is a huge load that should be we should take into account the first mission, but I think this difference will help us to provide even more optical resolution in the next mission. I don't see any more questions. If you have any questions about the lens, feel free to ask.
Okay, so I think that's all from our side. If I don't, if I could see, if there is any more question, you can ask them now. Okay, so if I don't see any more questions, so the last stuff or webinars left. So for those who are following our big prize, the prize clue from today webinars is chat with is CHED. If you don't know about what is going on, please visit our website and go to the small sat page. Thank you for participation. Thank you, Tomasz. Thank you, Piotr, for everything. If any of the participants have the other question, you can always contact with us by the email. And I just want to remind that this session was recorded for our training purpose. Thank you very much, and I hope so it was interesting. See you in the future, and have a nice evening or day, whatever your time it is right now. Thank you.
Thank you, guys.